Continue to the chapter number 5. So in this chapter we learn about counting methods. We start with basic principles in counting methods. In this lecture, in this topic, so we'll learn about the basic principles regarding addition and multiplication operations. So that means from these basic principles we can decide in certain conditions, so what kind of operations that we should use, whether using the addition operation, also the multiplication operation. So we can distinguish in which situation we should use the addition and in which situation we should use the multiplication. All right, so we start with this case. Okay, suppose we have a menu for the FSA cafe as shown in this table. So we have three kind of main menus. So we have appetizers, consists of nachos and salad, and then in the main course we have a hamburger, cheeseburger, fish fillet, and for beverages we have a tea, milk, cocoa, and root beer. Okay, so it features two appetizers, three main course, and four beverages. Okay, as shown in the previous table. So we have two kind of appetizers, three different main courses, and also four different beverages. Okay, we have the following example. How many different dinners contain one main course and one beverage? Okay, how many? All right, so this is the solution. So first of all, we have to use some notations to make our calculations easier. So we have a capital N for nachos, S for salad, and so on. All right, so we use these notations. Note that there are three main courses and four beverages. Okay, in the previous table we have three different main courses and four different beverages, and the question asks about in how many ways we can have different dinners consists of one main course, okay, one main course and one beverage. And in the menu we have three different main courses and also four different beverages. All right, so now we construct the following table based on this situation. So we have a main course, okay, three different main course in the first column, and in the second column we have a beverage. Okay, so for the main course we have a H for hamburger, C and F, and for beverage we have a tea, milk, cocoa, and root beer. Okay, so we can from this table we can pair, okay, each main course with different beverage. Alright, so we have H with T, H with M, H with C, and H with R. So I have the following combination. Okay, possible combination for the dinner. And for the main course C, we also can do the same task. We pair C with each four different beverages. So we have a CT, CM, CC, and CR. And we do the same thing to F. So we have FT, FM, FC, and FR. So we have the following four different combinations. Alright, so therefore back to the question, in how many ways we can have a dinner consists of one main course and one beverage. So there are 12 different dinners. 12 different dinners consist of one main course and one beverage as shown in the following column. Okay, we have a combination of HT, HM, HC, and HR, and also we have CT, CM, CC, and CR, and also we can have FT, FM, FC, and FR, where all these dinner combination are different combinations. There is no repetition, and all combinations are consisting of one main course and one beverage. Okay, so we move to the second example. How many different dinners consist of one appetizer, one main course, and one beverage? Okay, so we start from the appetizer. Okay, because we only have two appetizers, and then followed by main course because we have only three main courses, and then ended with beverages. Okay, because we have four different beverages. So we start with the appetizer. So for the appetizer we can pair N with all these different rows. Okay, we combine N with H, and H can be combined by another four different rows. Okay, and finally we combine all these three combinations and come out with the following combination. Okay, we have NHT, NHM, NHC, and HR, where each of these combinations contains of one appetizer, one main course, and one beverage. Okay, so we do the same task. Okay, we do the same task for another for the second appetizer. Okay, and then we pair S with H, S with C, and also S with F, and then followed by the combination with the following rows. We have another combination. All right, and finally at the rightmost column, so we have the following combinations contains of one appetizer, one main course, and one beverage. All right, so finally we combine, we count all the different combinations in the rightmost table. Okay, so from this column, okay, and finally we obtain there are 24 different dinners consist of one appetizer, one main course, and one beverage. Okay, we just simply add all the following different combinations. We do the addition operations. Okay, so in the menu there are 2 appetizer, 3 main courses, and 4 beverages. Therefore there are 2 times 4 times 2 times 3 times 4, which is equal to 24 different dinners consists of one appetizer, one main course, and one beverage. So from this example, the total number of dinners was equal to the product of numbers of each of the courses, appetizer, main course, and beverage. Okay, so because we have 2 different appetizers, 3 different main courses, and 4 different beverages, so we simply multiply all these numbers, okay, and come out with the product, which is 24, where 24 is representing the total number of dinners. Okay, total numbers of the dinners that which can be formed, consisting of one appetizer, one main course, and one beverage. So we have the following multiplication principle. If an activity can be constructed in t successive steps, okay, so where the first step can be done in n1 ways, okay, and the second step can be done in n2 ways, and then we proceed up to the t step, which is the final step, because we have t successive steps. So it is ended with the step number t, okay, the step t, and it also can be done in nt ways. Okay, so we have t successive steps, and each step can be done in n1, n2, up to nt ways respectively. Then the number of different possible activities, different. Okay, different possible activities. Different means there is no repetition. Okay, there is no repetition. Okay, the different possible activities can be computed as follows. So we just simply multiply all the possible ways, okay, all the possible ways together, and come out with the total number of different possible activities that can be done, okay, in these t successive steps. Okay, so in this scenario, or in this case, we use the multiplication principle. Okay, we use the multiplication principle. Okay, so we're back to the example number 1. Okay, the first step is to select the main course, and the second step is to select beverage. So if you recap the example number 1, our task is to come out with the total number of different combination of dinner contains of one main course and one beverage. Okay, one main course and one beverage. Okay, and this selection can be done in 2 successive steps, where the first step can be done in how many different ways? There are 3 different main courses, so that means the first step can be done in 3 different ways. And for the second step, how many different beverages? There are 4 different beverages, so that means the second step can be done in 4 different ways. Okay, so by using the multiplication principle, the total number of different possible dinner can be obtained by multiplying the number of ways the first task can be done, and also the number of ways the second task can be done, and finally we obtain the total number of different possible ways the task can be done. All right, there are 12 different menus contains of one main course and also one beverage. Okay, so how about the example number 2? In example number 2, we are doing the same thing. The only difference is we have a successive steps instead of two different successive steps. So in example number 3, we have three successive steps, which started by the first step is to select an appetizer. Okay, to select an appetizer, and the second step is to select a main course, and the third step is to select a beverage. Okay, so the first step, and all the steps can be done in successive ways. Okay, we start from first, second, and finally by third step. And the first step can be done in how many ways? There are two different appetizers. That means the first step can be done in two different ways. And for the second step, there are how many different courses? There are three different main courses. So that means the second step can be done in three different ways. And finally, the third step, which is to select the beverage, since there are four different beverages in the table menu. So that means this task can be done in four different ways. So as a conclusion, by using the multiplication principle, the total number of different possible dinners can be obtained by multiplying these three different ways. Okay, n1, n2, and n3, and come out with the total number of different possible ways this task can be done. So by multiplication principle, the number of ways of doing each step are multiplied together when an activity is constructed in successive steps. Okay, so that is for the multiplication principle. So now we consider another example. How many dinners consisting of one main course and an optional beverage? That means, okay, we can choose either one beverage or there is no at all beverage. Okay, so we may construct a dinner consisting of one main course and an optional beverage in two successive steps. The first step is to choose or to select the main course. Okay, and followed by the second step is which to select an optional appetizer. Optional appetizer, that means you have additional option for the appetizer. Originally, there are only two different appetizers. Okay, we have H. Okay, sorry, this one is for main course. Okay, sorry. So the first step is to choose the main course, and this task can be done in three different ways because we have three different main courses. All right, so we have H, C, and F. Okay, so the first step can be done in three different ways. So we can choose either H or C or F. Three different choices and three different ways to do the first step. Okay, we move to the second step. In the second step can be done in 5 different ways. Originally, we have only there are 4 different beverages. Okay, we have T, M, C, and R. Originally, in the original menu table, we have only 4 different beverages. But then, because the second task is either we can have one appetizer, one beverage, or there is no beverage. Okay, because it is optional. So we have additional option. Okay, which can be denoted by none. Okay, so the none can be represented by X, capital X. That means there is no selection for the beverage. So we have T, M, C, R, and none. So that means the second task can be done in 5 different ways. Alright, so that is why our N2 equal to 5. Okay, instead of 4, it is equal to 5. So by using multiplication principle, because this task can be done in 2 successive steps, So we can use the multiplication principle to come out with the total number of different possible dinners consisting of one main course and also optional beverage. So there are 15 different ways. Okay, so how to verify this answer? So we can construct the table. Okay, we can construct the table. Consists of the first column is the main course. Okay, because we have a smaller number of main course, so we start with the column main course followed by beverage. Instead of using 4 different rows, this time we have 5 different rows with additional option, which is capital X representing none. Okay, and then again we can combine, okay, all these possible menus and then come out with 5 different combinations. And then we proceed to the other selection of main course. Okay, we have a C. Okay, and also we can pay with all these 5 different options for beverages, and also for the F we can do the same thing. Okay, and finally we can add up all the selections. Okay, we have a 5 in here, 5 in here, and 5 in here. We can add 5 plus 5 plus 5, and also can be done using the multiplication principle. We have 3 times 5, which is equal to 15 different possible dinners. Okay, now we move to the example number 4. How many strings of length 4 can be formed using the letters A, B, C, D, E if repetitions are not allowed? If repetitions are not allowed. Okay, but that means the different combinations, we only allow different combinations of string, okay, with length 4 contains of letters A, B, C, D, and E. Alright, so we move to the solution part. So a string of length 4 can be constructed in 4 successive steps, because we have to choose the first string followed by the the first element in the string, followed by the first element in the string, followed by the second element, third, and also the fourth element in that string. So there are 4 successive steps. So we still start with step number 1, which is to choose the first letter. So the first letter, because we have 5 different characters, right? 5 different letters. So that means we can choose 5. We have 5 different options to do the first task. Okay, whether to choose A, to choose B, C, D, or E. So that means the first task can be done in 5 different ways. Okay, so we take 1 letter from the out of 5 letters. Okay, so because the repetition not allowed, so that means we have to take into account the number of letters that has been taken. So in the first step, we take 1 character as a selection for the first step. So the remaining characters, there are only 4 characters to choose in the next step. So in the step number 2, which to choose the second letter, so it only can be done in 4 different ways, because 1 character has been taken by the first step. So the second step can only be done in 4 different ways. Okay, because there are only 4 different characters remain. And then we move to the third steps, which to choose the third letter. And again, because we have to take out 2 characters out of 5 characters, so that means the remaining characters only 3. So the third task can only be done in 3 different ways. Okay, so the third step, which to choose the third letter, can only be done in 3 different ways. Okay, so we have taken 3 different letters, so the remaining letters, there are only 2 letters. Okay, and then the final step, because we want to construct a string of a length 4. So now we arrive at the final step, which to choose the 4th letter. And this 4th step can only be done in 2 different ways, because there only remain 2 different characters out of 5. So it can be done in 2 different ways. And then we have completed all the steps from the step number 1, 2, 3, and 4. Now is the time to do the multiplication principle, because this task can be done in 4 successive steps, and each step can be done in certain number of different ways. So we can do the multiplicative principle and come up with the total number of strings of length 4, okay, formed by using the letters A, B, C, D, and E, where repetitions are not allowed. Okay, so there are 120 possible combination of letters to form the string of length 4. All right. We move to the next example. How many strings? Again, how many strings in example 4 begin with the letter B? Previously, there is no such condition. In the previous example, we only have the question only asked to come out with a string of length 4 without any additional condition. Okay, the only condition given is there is no repetition allowed. But in this example, we are given another condition, and the condition is the first string, the first element of the string must start with the letter B. Okay, so this one is fixed. Okay, is fixed, and the other characters can be chosen from the given selections of character. Okay, so because we have A, B, C, D, and E, A, B, C, D, and E, and B have been taken as the first element in the string, the letter B has been taken as the first character in the string, so that means there are only 4 remaining characters or letters to choose. Okay, so the string of length 4 that begin with letter B, okay, which is constructed like this. Start with B, and we have another 3 empty spaces to fill. So this task can be constructed in 4 successive steps. So we start with the first step to choose the first letter, and the first letter is specified as choosing the letter B as the first element. So that means the first task can only be done in single way, because the question asks to do so. Only single selection for the first task, which is the letter B. So that means the first task can only be done in one way. Okay, in one way, since the first letter is fixed as B. Okay, finish with the first step, we move to the second step, and the second step is to choose the second letter. Okay, the second letter after we take B, so there are only 4 remaining letters, so that is why it can be done in 4 different ways. And then followed by the third step. The third step can only be done in 3 different ways, because the letter B and a letter in the second step have been taken out, so there are only 3 different characters to choose. So this task can be done in 3 different ways. And finally, the fourth step is to choose the fourth letter, and it can be done in 3 different ways, because there are only 2 different characters remain. So after we do all the successive steps, okay, to form a string of length 4, so that means there are 4 successive steps after we complete the fourth step. So it's time to use the multiplicative principle, because this task can be done in 4 successive steps. So we use the multiplicative principle. So there are 1 times 4 times 3 times 2 times 2, which is equal to 24 different strings of length 4 that start with the letter B. Alright, and then we move to the next example. How many strings of example 4 do not begin with the letter B? Okay, to answer this question, we have to recall back the answer for the first the example number 4, and also the answer for the example number 5. Okay, so we recall back the question in example number 4. We know that there are 120 different strings of length 4 that can be formed by using the letters A, B, C, D, and E. So that means with the string of length 4 with combination of the letters A, B, C, D, and E, there are 120 different strings. Okay, and in the example number 5, we put a condition where the first element in the string must be the letter B. So what does it mean? That means if we take out all the 24 strings that start with the letter B. So that means the remaining 96 are the combinations of string that start with other characters. Okay, with other letters. Okay, it can start with A, C, D, or E. There are 96 different possible strings of letter 4 that start either with A, C, D, or E. Okay, and also in other words, there are 96 strings that do not begin with the letter B. If we use the set the concept of set, so this is just like the complement. Okay, the complement set. Okay, so finish with the multiplication principle, the multiplicative principles, which can be applied when we're dealing with when the task can be done in successive steps, and each step can be done in different ways. Okay. Okay, now we arrive at the second principle, which is the addition principle. The addition principle tells us when to add to compute the total number of possibilities. In the previous principle, we learned about in the first principle tells us when to multiply to compute the total number of possibilities. So in addition principle, we learn about the principle when they tell us when to add to compute the total number of possibilities. Okay, so we proceed to the addition principle. Suppose that we have capital Xi up to capital Xt, and all these X are sets. Okay, so there are sets that the ith set Xi has ni element. Okay, the ith set Xi has ni elements. Okay, so if Xi up to Xt is a pairwise disjoint family. Pairwise disjoint family. So what does it mean? Pairwise disjoint family. So if we pair Xi and Xj, okay, where I not equal to j, so this intersection between these two sets Xi and Xj equal to an empty set. That means there is no common element in these two sets. Okay, in these two sets there is no common element. So what does it mean by pairwise disjoint family? So let's say I give you example. So we have three different sets. Okay, let's say X and 1, X and 2, and X and 3. Okay, where the set X and 1 contains N1 elements, set X and 2 contains N2 elements, and set X and 3 contains N3 elements. Okay, so if we do the intersection among these three sets, let's say we start with X and 1 intersect with X and 2, so the result is an empty set. That means there is no common element between these two sets. Okay, so that means these two sets are disjoint set. Okay, and then we move to the second combination. X and 1 intersect with X and 3. Again, there is no intersection because these two sets are disjoint sets. Okay, and finally we arrive at the third possible combination with it, which is n X and 2. We intersect with X and 3. Again, there is no intersection because the result is an empty set. That means there is no intersection between these sets. Okay, there is no common element in these two sets. So from these three different combinations, we can say that X and 1, X and 2, and X and 3 as a pairwise disjoint family. Okay, so because the intersection are commutative, so we can say that X and 2 intersect X and 1 are equal. Okay, so there's no need to repeat because they are representing the same thing. Okay, so you just have these three different combinations of intersection. So because all these three possible combinations result the same set, which is the empty set, so that means this set or this xn1, xn2, and xn3 are pairwise disjoint family. All right. So the number of possible elements, that can be selected from x1 or, okay, or x2 or up to or xt is n1 plus n2 plus up to plus nt. So in our case, in our example, that means the number of possible elements that can be selected from xn1 or xn2 or xn3 is n1 plus n2 plus n3. Okay? Equivalently, the union x1 union x2 up to union xt contains n1 plus n2 plus up to n plus n3 nt elements. Or in our example, okay, the union of xn1 plus xn2, the union of xn1 union xn2 union xn3 n3 contains n1 plus n2 plus n3 elements. All right, so this is what is the addition principle about. Okay, so we add the numbers of elements in each subset when the elements being counted can be decomposed into disjoint subsets. Okay, so if we can do that, that means we can use the addition principle. Okay, the addition principle. So we add the numbers of elements in each subset, xn1, xn2, xn3, and so on, when the elements being counted can be decomposed into disjoint subsets. If we are counting objects that are constructed in successive steps, we use the multiplication principle. And if we have disjoint sets of objects and we want to know the total number of objects, that means we have to use addition principle. So I highlighted the important keywords, okay, for the multiplicative principle. The keywords is successive steps, while for the addition principle, the keywords is the disjoint sets. Okay. Okay, now we move to the next example, how we can use the addition principle. So we consider the following example. How many 8-bit strings begin either? Okay, either means or. Okay, either 101 or 111. Okay, so that's the solution. How many 8-bit strings, string of length 8, okay, begin either 101 or 111. That means the end of these strings can be any combinations. Okay, we only fix the first 3 elements in this 8-bit strings. Okay, look at the solution. An 8-bit strings begins 101 can be constructed in 5 successive steps. Okay, so we have we put the starting elements in front, and we let the remaining elements as an empty space to be filled. We start with the first step, which to select the 4th bit, so it can be chosen because this is binary, so the possible element in there is either 0 or 1, so that because we have 2 different selections, so this task can be done in 2 different ways. Either we choose 0 or we choose 1. We move to the second step, okay, to select the 5th bit. So it also can be done either we choose 0 or to choose 1. And then same goes with the 6th step, either to choose 0 or 1, followed by the 4th step to choose the 7th bit, either we choose 0 or 1, and finally the 5th step, which to select the 8th bit in this binary string. So it also can be done whether to choose 0 or 1. So note that each of the 5 bits can be selected in 2 ways, either 0 or 1. Okay, all these steps can be done in only 2 different ways, either to choose 0 or to choose 1. So because the steps can be done in successive ways, okay, or in successive steps, so we can use the multiplication principle. So there are 2 times 2 times 2 times 2 times 2, which is equal to 32, is the total number of different combination of bits. Okay, so what does it mean? There are 32 8-bit strings that begin with 101, and then the second task, okay, is to construct the 8-bit strings that begins with the number 111. Okay, just like the previous step, we only change the elements in front as 111, and we leave the other 5 strings as an empty space to choose either 0 or 1. Okay, in this 4th step, 5th step, 7th step, 8th step, and 8 steps, all the steps can be done into different ways respectively, either to choose 0 or to choose 1. So note that there are 32 8-bit strings that begin 101 and 32 8-bit strings that begin 111. Okay, that is our conclusion. So how to answer this question? So we can use the addition operation. Okay, addition operation. So we just simply add 32 plus 32. There are 64 8-bit strings that begin either 111 or 101 or 111. So why we can choose the addition operations? Because we are dealing with disjoint sets. Okay, because there is no string that can start with 101 and 111 at the same time. Okay, it's impossible. Okay, so the string can either be start with 101 or 111. It cannot be start the string cannot start with the combination 101 and 111 at the same time. Cannot. So it is either start with 101 or start with the string 111. So that means we have two separated sets, and these sets are totally disjoint sets. So that is why we can use the addition operations to come out with 64, representing the number of 8-bit strings that can be constructed that begins either 101 or 111 as the first 3 elements. Okay, in example 4, we could let x1 denote the set of 8-bit strings that begin 101, and we denote x2 as the set of 8-bit strings that begin with 111. Since x1 is disjoint from x2, okay, there is no common element between these two sets. So x1 is disjoint from x2. So according to the addition principle, the number of 8-bit strings that begin either 101 or 111, which is the number of elements in x1 union x2, is equal to n1 plus n2 equal to 64, because there are 32 different elements in x1 and also there are 32 different elements in x2. So there are 64 different strings that start either 101 or 111. Okay, we proceed to the example number 5. In how many ways can we select 2 books from different subjects among 5 distinct science books, 3 distinct mathematics books, and 2 distinct graphics book? Okay, look at the solution. So by using multiplication principle, we can select 2 books, one from science and one from mathematics, in 5 times 3 different ways, because there are 3 distinct mathematics books, and also there are 5 different science books. So the first task can be done in 15 different ways. Okay, because the first task can be done in 5 different ways, and the second task can be done in 3 different ways. So total up there's 15 possible ways to accomplish the first task. And we move to the second task to choose 2 books, one from science and one from graphics. So there are 5 times 2, which is equal to 10 different ways. And finally, the combination, we have 2 books consists of one from mathematics and one from graphics. So because these steps can be done in two successive steps, you start with selecting a book or a mathematics book and followed by selecting a graphics books. So this task can be done in 3 times 2 different ways, because there are 3 different mathematics books and also 6 different and 2 different graphics books. So total up there are 6 different ways. So note that the set of selections are pairwise disjoint. Okay, so all the sets of selections are pairwise disjoint. There is no common element among these 3 sets. So because we have 3 different disjoint sets, so we can use the addition principle to add up all these 3 combinations, and finally we have 31 different ways to select two books from different subjects among science, mathematics, and graphics books. So from all these early examples, so we can conclude the following solving tips. Use the multiplication principle when using the base step-by-step process to construct an activity, and we can use the addition principle when you want to count the number of elements in a set, and you can divide the set in non-overlapping or disjoint subsets. Okay, now we move to permutation. And ordering of object is called a permutation order. Okay, that means the position of object. Okay, the position of object, which one is the first element, followed by second, and also the next element. Okay, so the ordering of object is called as permutation. A permutation of n distinct elements denoted as x1 up to xn is an ordering of n elements consists of 1, x1, x2 up to xn. Okay, so that is what we call as permutation. We consider the first example. How many permutations of 3 different elements A, B, and C? So there are 6 permutations of 3 different elements of A, B, and C listed as follows. So we have all these 3 combinations. We have A, B, C, A, C, B, B, A, C, C, B, A, C, A, B, and C, B, C, B, A. And all these combinations are unique. There is no repetitions. Although all these objects are consisting of the same characters A, B, and C. Okay, so in permutation we have A, B, and C totally different with A, C, B, because in this elements, okay, in this combination, okay, so the orders matter. Okay, the position of A, B, and C in these elements are very important. Okay, ataupun or matter. Okay, so we have the following theorem. There are n factorial permutations of n different elements. There are n factorial. Okay, there are n factorial, the total number of permutations of n elements. So we consider the next example. How many permutations of 10 elements? So we have 10 different elements, and the question asks us how many permutations. So as the answer, there are 10 factorial, because we have 10 elements. So there are 10 factorial, which is equal to 10 times none up to times 1, which is equal to 3,628,800 permutations of 10 elements. Okay. Next, we move to the example number 3. How many permutations of letters A, B, C, D, F contain substrings D, E, F? Okay, so we have additional condition where the string D, E, F must stick together, okay, in the D, E, F form. Okay, so the letters D, E, and F must stick in a single combination, which is D, E, and F, D, E, F. So this is the solution to guarantee the presence of the pattern D, E, F in the substring. Okay, so it must be kept together in this order. So D, E, F must be the letters D, E, and F must be combined together in the arrangement of D, E, F. Okay, so it must be kept together in this order. The letters A, B, and C can be placed arbitrarily. okay, in other position. So the letters A, B, and C can be placed arbitrarily. So we can think of constructing permutations of letter A, B, C, D, E, F that contains the pattern D, F by permuting 4 tokens. Okay, this one is the first token, this is the second token, the third token, and the fourth token. Okay, so because there are 4 different tokens, so that means it can be done in 4 factorial, which is equal to 24 permutations of 4 objects. Okay, where DEF is considered as one object. Therefore, the number of permutations of the letters A, B, C, D, E, F that contain substring DEF is equal to 24. Sometimes we want to consider an ordering of R elements selected out of n available elements. So that means we want to consider only part of the elements out of the total number of elements. So we denote the element as R, where R much less than or equal to n. Okay, so such permutation is called R permutation. Okay, so this is the definition for the R permutation. An R permutation of n distinct elements x1 up to xn is an ordering of an R element subset of x1 up to xn. Okay, originally we have n distinct elements x1 up to xn, but then we only want to consider R out of this n object. Okay, so that means we are dealing with R permutation. So the number of R permutations of a set of n distinct elements is denoted by capital P, and in parentheses we have n, which is the total number of elements, and also R, which is the number of sub elements out of n different elements. So P and R. Okay, so P and R. So we consider the theorem to formulate the P and R. So the number of R permutations of a set of n distinct objects is P and R equal to n times n minus 1 times n minus 2 up to times n minus R plus 1. So this can be formulated as equal to n factorial divided by n minus R factorial, where we need to make sure that the value for the R is always less than or equal to n. Okay, so we start with example number 4. The number of 2 permutations of the set X equal to ABC. So that means our R equal to 2 and our N equal to 3. So the R permutation is P32, because our n equal to 3 and our r equal to 2. So we have P32 equal to 3 factorial, which is n equal to 3. So we have n factorial divided by 3 minus 2. So n minus r equal to 3 minus 2 factorial. Okay, so which is equal to 3 factorial because the denominator is 1 factorial, which is equal to 1. So we have the 3 factorial. So 3 factorial means 3 times 2 times 1, which is equal to 6. So that means there are 6 2 permutations which can be listed as follows. We have AB, AC, BA, BC, CA, and CCB. Okay, now we move to example number 5. In how many ways can we select a chairperson, a vice chairperson, a secretary, and a treasurer from group of 10 persons? Okay, so look at the solution. So we need to count the number of ordering. Okay, the number of ordering of 4 persons selected from a group of 10 persons. So the order is, we start from the first one is the chairperson, followed by the second position is the chairperson, vice chairperson, the third position is secretary, and the fourth position is the treasurer. Okay, so that means we have to arrange these 4 persons in one arrangement. So the first one is the chairperson, followed by vice chairperson, secretary, and treasurer. So that means we need to count the number of ordering of 4 persons. Okay, and these persons are selected from a group of 10 persons. So Obviously, we have our permutation case, so we have to permute. We have to do the permutation 4 out of 10. So that means we have 4 permutations of 10%, which is equal to P104. So P104 equal to 10 factorial because our n equal to 10 over 10 minus 4 because our n equal to 10 and our r equal to 4. So n minus r is equal to 10 minus 4 factorial. Then we have 10 factorial over 6 factorial. So we can compute using your calculator. So there are 5040 different orderings. Okay. Next is combination. So previously we have a permutation, okay, where the orders matter, and in combination, again we have to select an object, but this time we have to select objects, but this time without regard to order. That means the order do not matter. Okay, so without regard to order, so this kind of selection is called a combination. Okay, that means the order doesn't matter. So this is the proper definition for the combination. Given a set of x contains x1 up to xn. Okay, so this set containing n distinct elements. Okay, we have x1 up to xn, so there are n distinct elements. And R combination of x is an unordered selection of R elements of x. Okay, that is an R element subset of x. And the number of R combination of the set of n distinct elements is denoted by C and R. Okay, just like the R permutation denoted by capital P and R. So this time we are dealing with combination, so it is denoted by C and R. Okay, just the R combination. So based on this theorem, okay, we can compute the R combination by using the following formula. We have C and R equal to n factorial over n minus r factorial, and then we multiply with r factorial. Okay, and we need to make sure that the r must less than or equal to n. Okay, so we consider the following example. A group of 5 students, Mary, Boris, Rosa, Ahmad, and Nguyen, has decided to talk with Mr. Alex about discrete mathematics course, and Mr. Alex has said that he will speak with 3 of students. Okay, only 3 students out of 5 students. So in many ways can these 5 students choose 3 of their group to talk with Mr. Alex. So first of all, we need to consider about the order. Is the order matter or not? So in this case, is it the same if Mr. Alex talked to Mary, Boris, and Rosa, or Mr. Alex talked to Rosa, Boris, and Mary? So actually they are same students. Okay, they are same students. So that means the order doesn't matter. Whether M comes first, B comes later, and followed by R, still representing the same people or same students if we write as R, B, N, and M. That means order doesn't matter as long as Mr. Alex, because Mr. Alex want to talk with only 3 students. Doesn't matter about the order, who's the first, second, and third, but only the condition is 3 different students out of 5 students. So obviously we are dealing with R combination case, okay, and not R permutation because the order doesn't matter. In this case, it will make no difference whether Mr. Alex talked to Mary, Ahmad, and Nguyen, or to Nguyen, Ahmad, and Mary. Okay, so that means the position of these 3 students doesn't matter. Okay, thus we must not take order into account. That means order doesn't matter. So the number of ways the 5 students choose 3 of them to talk with Mr. Alex is a 3 combination and not 3 permutation. Okay, so we denote it as capital C 5 3 because our n equal to 5 and our r equal to 3. So it can be computed by using this equation. So finally the answer is equal to 10. There are 10 possible combination of students. Okay, 3 students out of 5 to talk with Mr. Mr. Alex. So we can list down all these combinations. So if the question doesn't ask you to list down, so no need to list down all the combinations. You simply provide the total number of combinations. But then if the question asks you to do so, so we have to list down all the combinations. Okay, we need to list down all the combinations. So it's up to the question whether the question asks to list or not. Okay. Right. Example number 7. In how many ways can we select a committee of 3 from a group of 10 distinct persons? So again, we are required to form a committee, but this time uh, there's no position. That means there is no condition to be a chairperson, vice chairperson, secretary, or treasurer. Okay, the condition is only 3 committee. Okay, out of 10 distinct persons. Again, that means the order doesn't matter in this case, because there is no specific position for all this committee. Since a committee of an unordered group of 3, okay, that means the order doesn't matter. Whether we have A, B, C, it is also equal to C, B, A. Okay, the same combination, so that means order doesn't matter. Since a committee is an unordered group of people, so we are dealing with 3 permutations, because we have to form 3 out of 10. So combination of C 10 3, which is equal to 120 ways. Okay, example number 8. In how many ways can we select a committee of 2 women? This time we specify 2 women and 3 men from a group of 5 distinct women and 6 distinct men. Okay, let's see how to solve this problem. We can find the 2 women. Okay, we can find the 2 women can be selected in combination of 5 2, because either we choose woman A and then followed by woman B, it is always equal to we choose the woman B followed by woman A. Okay, so this is a 2 combination out of 5. So C 5 2 equal to 10, and the second step is to choose the man, and the man can be selected in 20 ways, because it is a 3 combination out of 6. So C 6 3 equal to 20 ways. Okay, and then we conclude that the committee can be constructed into successive steps. We choose the woman first and followed by the selection of men. That means this task can be done into successive steps, and each step, okay, the first step can be done in 10 different ways, while the second step can be done in 20 different ways. So according to the multiplicative principle or multiplication principle, so the total number of committee is equal to 10 times 20, which is equal to 200. So we use the multiplication because the task can be done in successive ways. Okay, now we discuss about factorial functions. So in the previous topic, in the permutation and combination, so we deal with the factorial operation actually. So factorial is a function. Okay, it's a function which called as factorial function. The product of all consecutive integers up to a given integer occurs so often in mathematics, and it is given a special name or special notation called the factorial notation. So for definition of the factorial, for a whole number n, the quantity n factorial denoted as n factorial. So n can be whole number. That means the smallest possible value for the n equal to 0. Okay, so it can up from 0, 1, 2, 3, and so on. The smallest element is 0. That means we have a 0 factorial. 0 factorial is defined, and it is defined as equal to 1. Okay, so this one is considered as special definition. Okay, as a special definition. All mathematicians agree that 0 factorial is defined equal to 1. Okay. So the factorial is defined as the product of all integers from 1 up to n. So n factorial equal to n times n minus 1, n minus 2 up to times 1. Okay, so the question without using calculator, simplify the following expression. So we have 8 factorial over 7 factorial. Okay, so 8 factorial means 8 times 7 times 6 times 5 and so on up to times 1. Okay, 7 factorial means 7 times 6 times 5 up to times 1. So from that, we know that 8 factorial, okay, equal to 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So all these parts can be represented by 7 factorial. Okay, so that means 8 factorial equal to 8 times 7 factorial. So we can replace the 8 factorial as 8 times 7 factorial, and at the denominator we also have 7 factorial, so we can cancel out. So we know that the answer is the remaining value equal to 8. 8 times 1 equal to 8. Okay, and then in the second one we have 5 factorial over 2 factorial times 3 factorial. Okay, again, in the numerator, so we can simplify the numerator until we can cancel out with the denominator. So we have 5 factorial, it is equal to 5 times 4 times 3 times 2 times 1. So 5 factorial is equal to 5 times 4 times this one can be represented as 3 factorial or simplified as 3 factorial. So at the denominator we also have 3 factorial. So this time we can, because 2 factorial is simple, it is equal to 2, so we can simplify it, the fraction as equal to 20 over 2 equal to 10. Okay, next is additional of two fractions. So we have one addition of two fractions. So we have 1 over 2 factorial 4 factorial plus 1 over 3 factorial 3 factorial. All right. So the first step is to make the denominator as equal value. Then we can proceed with the addition of fractions. So how to do that? So to make the denominator equal, so we can multiply both sides, both fractions by 3 and 4. Okay, 3 over 3 and 4 over 4. So the equation remains true because actually this fraction equal to 1 and this fraction also equal to 1. So that's why we still can maintain with this equal sign. Okay, and then we multiply the first fraction. So actually at the numerator we have 3. 1 times 3 equal to 3. And at the denominator, so because we have 3 times 2 factorial times 4 factorial, so this part actually can be simplified as equal to 3 factorial. Okay, because 3 factorial is equal to 3 times 2 times 1, and this one is 2 factorial. So that's why we replace this 3 times 2 factorial equal to 3 factorial. On the other side, so we have 4 times 3 factorial. So again, this one also can be replaced as 4 factorial. Okay, so obviously we have a similar value for the denominator. We have 3 factorial times 4 factorial, which is exactly equal to the 4 factorial times 3 factorial. So we can proceed with the addition operation on fractions. So we can add the numerator 3 times 4 and denominator maintains as 3 factorial 4 factorial. Okay, and then we can because this fractions is in the simplest form, so we can proceed with the calculation. So we obtain the fraction is equal to 7 over 1 4 as the final answer. Next is n plus 1 factorial over n factorial. Okay, so again, n plus 1 factorial, actually just like in the previous example, we have 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1, which is equal to 6 times 5 factorial. Okay, so this time we have n plus 1 factorial. So we have n plus 1 multiply with n plus 1 minus 1. So just like this, 6 multiply with 6 minus 1 factorial. So n plus 1 multiply with n plus 1 minus 1 factorial. Okay, at the denominator, just like the this case. Okay, this case. Okay, so at the denominator we maintain is n factorial, and then we expand this parenthesis. So we have n plus 1 minus 1. The remaining value is equal to n factorial. So we can cancel out because at the denominator we have n factorial. So we can cancel out these two parts. So the remaining value is equal to n plus 1 as the simplest form of the following fraction. Next is n factorial over n minus 3 factorial. So again, we can simplify by cancel out the denominator. So how to come out with the denominator element in the numerator part? So we can simplify the n factorial as n times n minus 1 times n minus 2 times n minus 3 factorial. Okay, just like 5 factorial, which is equal to 5 times 4 times 3 times 2 times 1. So we have 5 times 5 minus 1 times 5 minus 2 and times 5 minus 3 factorial. Okay, so we can do the same thing here. So we have n times n minus 1 times n minus 2 times n minus 3 factorial, and then this part can be cancelled out because at the denominator we also have n minus 3 factorial. So the remaining elements are n times n minus 1 times n minus 2, which can be expanded, becomes this cubic equation. Okay, so because we're dealing with factorial functions, so now we are ready to discuss about the binomial theorem. Okay, so we consider the following definition. Okay, let n and r be whole number. That means the smallest possible value for these numbers equal to 0. Okay, so n and r are whole number with r is restricted to be less than or equal to n. Then nr is equal to ncr, which is equal to n factorial over r factorial times n minus r factorial. So this is called, or this is read as n choose r. That means from from n elements we choose only r. Okay, or simply called as n choose r. So it represents the number of subsets of size r that can be chosen from a set of n elements. Okay, so this is the equation for the n choose r. Okay, we consider the following example. By showing the calculation steps, compute the following. We have 8c5. 8c5 is equal to 8 factorial over 5 factorial times 8 minus 5 factorial. It can be simplified, become this fraction, and this fraction can be computed as 56. And then for the n plus 1, so remember in our formula we have nr. Okay, so we have to consider that all the elements appear at the top of this parenthesis as n. Okay, so we can substitute all n in the formula as n plus 1 factorial. Okay, back to the formula. What is the formula? N factorial over r factorial n minus r factorial. Okay, this is for nr. So this time at the top we have n plus 1. So we have to substitute all the n. Okay, n with n minus r. Okay, sorry, n plus 1. So we have n plus 1 factorial. Okay, and at the denominator we also have n plus 1 to substitute this n. So how about the r? Because in the r position we have n, so we have to substitute all r in this original formula as n. So we have n factorial, and also we have n here. Okay, so after we complete all the element or all the entries in the formula, so now we are ready to simplify the formula. So it is equal to n plus 1 factorial is equal to n plus 1 times n factorial divided by n factorial So n plus 1 minus n can be simplified, becomes only 1 factorial because n minus n can be cancelled out. So the remaining value is 1 factorial. So because we have a common element at the denominator and numerator and denominator, so we can cancel out this one and this one. So the remaining element is n plus 1. Okay, now we proceed to the next example. Prove the following. So the n choose r equal to n choose n minus r. Okay, so to show this equations true, so we need to prove that the left hand side equal to right hand side. Okay, and we need to refer back to the original formula for the n choose r. Alright. Okay, at the left hand side we have n choose r equal to this formula, and at the right hand side we have n choose n minus r. So that means in this formula, okay, we have to substitute all the n, okay, n factorial over r factorial n minus r factorial. So in this position we have at the top we have capital N, so we maintain all the n in this formula. But then at the bottom we have n minus r, so that means we need to replace all r by n minus r. So we have n factorial, n minus r factorial, n minus r factorial. And then we simplify. Okay, this one can be simplified, becomes n minus n. This one, pardon, this one is supposed to be plus, okay, because minus times minus equal to plus. So n minus n plus r factorial, the remaining value is r factorial. So we can simplify, we notice that this equation exactly equal to this equation, so we can conclude that the left hand side equal to right hand side, which completes the proof. Next, okay, we have to prove that n minus r plus n choose r plus n choose r plus 1 equal to n plus 1 choose r plus 1. Okay, again we have to refer to the original formula. So at the left hand side we have n choose r plus n choose r plus 1. So we plug in these values into the we insert these values into the formula. So for this first one we use the original formula, and for the second one we use the formula by replacing the r by r plus 1. Okay, so this one r plus 1, this one also replaces as r plus 1, and then we simplify. Okay, because we have addition operation on fractions, so we have to make sure that the denominator are exactly the same. Okay, so how to do that? So we multiply both fractions. Okay, the first fraction by r plus 1 over r plus 1, and the second fraction we have n minus r. Okay, so we take common element here actually, n minus r and r plus 1. So the equation remain true because this one equal to 1 and this one also equal to 1. Okay, so that is why we can maintain the equation notation there, because the equation remains true. So we expand the parenthesis, okay, the multiplication. So we have the following equation. So as you can see, at the denominator can be simplified. Okay, so r plus 1 times r factorial actually equal to r plus 1 factorial. Okay, and also n minus r times n minus r minus 1 factorial is equal to n minus r factorial. Okay, so obviously we have two fractions with a common denominator, so that means we can proceed with the addition operations on these two fractions. So it equal to this single fraction now after we do the addition operation. So now is the time to simplify this fraction. Okay, so to simplify this fraction, so we have r plus 1 n factorial plus n minus r n factorial over r plus 1 factorial times n minus r factorial. So we can expand the parentheses, we multiply inside. Okay, so we have the following equation, and then again we simplify. Okay, because this part and this part can be cancelled out, so the remaining elements are n factorial plus n factorial. Okay, So because we have a common elements here, so we can factorize, so it becomes n factorial times 1 plus n. Okay, and then n factorial and n plus 1. So what does it mean? That means it is equal to n plus 1 factorial. Okay, this one 1 plus 1 factorial. So at the denominator we try to we try to simplify the denominator. So r plus 1 actually can be substituted as n minus r plus 1 minus 1, and this one can be simplified. So the remaining elements is n plus 1 minus r in parenthesis r plus 1. Okay, so actually this part, okay, if we look at the formula is n factorial. We have r factorial n minus r factorial. This is the original formula. So if we replace n by n plus 1, so we replace r by r plus 1, so actually we obtain the following fraction. Okay, if we substitute n by n plus 1 and we substitute r with r plus 1, so actually we have the following equation, which is equal to n plus 1 choose r plus 1. So since left hand side equal to right hand side, so it completes the proof. Okay, now we have the following theorem, which is the application of the binomial theorem. So let's say we have a and b are real numbers and n be a positive integer. Then we have a plus b to the power of n can be computed by using the following equation. The expansion of a plus b to the power of n can be computed by using the following equation. So when we do the expansion, for example, when the power is low, okay, we have 1 plus x square or 1 plus x cube. So for this task, it's no problem to us because we can do the expansion easily. 1 plus x or multiply 1 plus x, and this one also can be done easily by expanding 3 parentheses, 1 plus x times 1 plus x times 1 plus x. But when the power getting higher and higher, it's quite difficult for us to do the expansion. So luckily we have this equation. We can use the binomial theorem to accomplish this task, okay, by using this formula. Alright, so this is the formula. So we start with the first example. Determine the expansion of 2 plus x to the power of 5. Okay, so from this parenthesis we have to identify our a, our b, and also our n, because all these values have to be inserted into this equation. Okay, we need to identify correctly what is our a, what is our b, and what is our n in order to use this formula. Okay, so to solve this problem, we have a equal to 2, b equal to x, and our n equal to 5. And then we insert into the formula. So we have first 5 choose 0 times 2 to the power of 5 minus 0 times x to the power of 0, followed by x choose 1 multiply by 2 to the power of 5 minus 1, x times 1 to the power of 1, all the way up to x, all the way up to 5 choose 5 multiply 2 to the power of 5 minus 5, x to the power of 5. Okay, so we simplify by using the formula of binomial theorem. Okay, so we have the following equation actually. So we have a 5 choose 0. Okay, we have 5 choose 1, 5 choose 2, up to 5 choose 5. And the power for the x, actually we have the highest power for the x is equal to x to the power of 5. Okay, so this one can be computed by using the formula. Okay, we have n factorial, r factorial, n minus r factorial. Okay, our n and our r, in this case our n equal to 5, our r equal to 0. So we can compute the value equal to and then we multiply with 2 to the power 5, so we have the value equal to 32. Okay, so there is no value for the there is no value for the there is no power for the x, so there is no element x in here. Okay, there's no x, so we have 32 only. So for the rest, so we have x to the power of 1, x to the power of 2, x cubed, x to the power of 4, and x to the power of 5 as the highest power. Okay, so this is the expansion. Okay, this is the expansion. Next, we have 1 minus 2x to the power of 4. Okay, again, we need to identify what is our a, b, and also our n. So in this case, our a equal to 1, our b equal to negative 2x, because we have to stick with the original form of the formula, a plus b. Okay, so in this case, 1 plus negative 2x to the power of 4. So that means our a equal to 1, our b equal to negative 2x, and our n equal to 4. And finally, we can use the following formula to compute the expansion. Okay, because the power is equal to 4, so the highest power for the x is equal to x to the power of 4. Okay. And then in this example, the question asks you to find the term, okay, the term in the binomial expansion. Find the third and the sixth term of the binomial expansion a plus b to the power of 8. Okay, to the power of 8. Okay, we start with the first task to compute the third term. So the third term is equal to 2 plus 1 term. Okay, 2 plus 1 terms. Thus, our r is equal to 2. Okay, so how do we know the r is equal to 2? So we're back to the original expansion actually. Okay, so this is the original expansion. So in this expansion, we need to identify what is the first, second, and third element. Okay, so this one is the first, this one is the second, and this one is the third. Okay, in the third term, so that means our r is equal to 2. Okay, so this is the formula for the third term. Okay, n choose 2, a to the power of n minus 2, b to the power of 2. So this is the third term. Okay, so that means our r equal to 2. So this is the formula to compute 8 choose 2 times with a to the power of 8 minus 2 times b square, so it is equal to 28 times a to the power of 6b square. So this is the third term in this expansion based on the binomial expansion. And how about the sixth term? So the sixth term, okay, we can generalize this one. It becomes 5 plus 1 because the third term is 2 plus 1. So the sixth term is 5 plus 1. So that means our r equal to 5. So back to the binomial expansion formula. So for the 8, choose 5. We multiply with a to the power of 8 minus 5. We multiply by b5. So we compute this one. So finally, the outcome is 56 a cubed b5. So this is the sixth term in the binomial expansion of a plus b to the power of 8. Okay, in the previous example, the question asks you to find the third and sixth term. Okay, so in this example, the question asks you to identify the coefficient of y5 and x6 in the expansion of x plus y to the power of 9. Okay, so to answer this question, we have to find the coefficients. What are the coefficients that is combined with the term y to the power of 5 and also with the term x to the power of 6? Okay, so we gathered information from the given question. First of all, we note that the value for the n equal to 9. Okay, so from that, we know that the r term, the r plus 1 term can be computed by using this formula. Okay, the r plus 1 term. So when the formula is for the r plus 1 term, so we insert the value for the r here. 9 choose r, multiply with the x to the power of 9 minus r, y to the power of r. Okay, so here we have y to the power of r, and the question asks you to find the coefficient for the y to the power of 5. That means we can replace the value for the r equal to 5. Okay, to find the term for the y, 5. So after we replace r equal to 5, so we have the following equation, which can be simply computed, equal to 1 to 6x4 y 5. Okay, so the answer for the first question is the coefficient of the y5 is equal to 126 x to the power of 4. So that is the answer for the first question, because the question asks you the coefficients, so you have to give the coefficient. Okay, finish with the first one, we move to the second one. We have to find the coefficients that combined with the term x to the power of 6. So we back to this the formula. In the formula, how we can come out with the value for the x equal to 6. Okay, so in the formula we have x to the power of 9 minus r. So our aim is to obtain x to the power of 6. So because we only have the unknown is r, we don't know what is the value for the r to be inserted into this equation. So we can find the value for the r by solving this equation. X to the power of 9 minus r equal to x to the power of 6, because we have a common element here as the base, so we can solve the exponent value. So we have 9 minus r equal to 6, which can be solved for r equal to 3. Okay, so we know the value for the r equal to 3, so it's very easy for us to use this equation to insert the value for the r equal to 3 and come out with the coefficient for the x, 6. Okay, so we have to conclude our answer to answer the question. So we have to provide the coefficient for the y5 and also the coefficient for the x6. So therefore, the coefficient of y5 equal to 1 to 6x4 and the coefficient for the x6 equal to 84y cubed. So remember, in order to answer this kind of question, you have to provide the conclusion for the final answer to completely answer the question. Next, find the coefficients of P4 and Q5 in the expansion of P plus Q to the power of 10. Okay, so from the given question, we have the following information. We note that our n equal to 10, and to compute the r plus 1 term, so it can be computed by using the following equation. So 10r multiply p to the power of 10 minus r, we multiply with q to the power of r. Okay, the question asks for the coefficient of P4 and P5. So we do the same task. Find the way how we can come out with the coefficient to the power of P4 and also the question of Q5 based on the following equation. So for the Q, it's very easy. It's straightforward. So we just simply substitute the R equal to 5. Okay, so R equal to 5. Then we obtain Q to the power of 5. So we compute the part here. So finally, we obtain the coefficient for the Q5. For the P4, okay, we have this term, P to the power of 10 minus R. So we want it becomes P to the power of 4. So we pair these two as equation. So because we have the same base, so we just focus on the exponent value. So we solve the exponent value. 10 minus r equal to 4, which can be solved as r equal to 6. And we insert into the equation. And then we obtain the coefficient for the P4 as 210Q6. And don't forget to conclude your answer, because the question answer you the coefficients. Okay, not the whole term. Okay, the question asks you the coefficients, so you need to provide the coefficients in order to complete the answer. Okay, next, determine the terms independent of x. Independent of x means the term without the term x. Okay, now the element without the term x. Determine the terms independent of x in the binomial expansion x plus 1 over x to the power of 8. Okay, from the given information, we know that the original formula is a plus b to the power of n. So we have our a equal to x, our b equal to 1 over x, and our n equal to 8. Thus, the r plus 1 term is computed by using this formula, and choose r, x to the power of 8 minus r times 1 over x to the power of r. Okay, so which can be simplified like this, because 1 over x can be substituted as x to the power of -1, and then we multiply r inside, so it becomes x to the power of -r. Okay, so because we have a same basis, x and x, so using the exponential law, so we can combine together. Okay, we can combine together because the operations of multiplication, so we can add the exponential term. Okay, it becomes 8 minus r, and then which can be simplified as x to the power of 8 minus 2r. The term independent of x means that the power for the x equal to 0, because whenever x to the power of 0, so it becomes the value becomes 1. Okay, so because we have the same basis in this equation, okay, so we just focus on the exponential value. So we have n minus 2r equal to 0, so we just simply solve for the unknown r equal to 4. Okay, so back to the original this one. Okay, so we have n choose 4, n choose r as 8 choose 4, so 8 choose 4 is equal to 70. All right, because this r, the exponent value already equal to 0, so we only focus on this part, so that part is equal to 70. So 70 is the term that is independent of x in the given binomial expansion. Okay, we consider the following theorem. Let's say n be a negative integer or n be a quotient. Okay, be a rational number, that means quotient. So previously we deal with the binomial expansion when the power is a positive number, okay, or whole number, 0, 1, 2, and so on. But this time we deal with the negative value of n, and also when the value for the n is fraction. Okay, so what is the expansion? Okay, so we have the following theorem. So for the 1 plus x to the power of n, so this is the general term, 1 plus x to the power of n. So the expansion when n is a negative number, or when x is a fraction number, so it is equal to 1 plus nx plus n minus n minus 1, minus n minus 1 over 2 factorial multiplied by x squared, and a plus n times n minus 1 times n minus 2 over 3 factorial multiply with x cubed plus and so on. So don't forget to put this triple dot. That means there are more and more elements after this addition sign. Okay, so don't forget to put this triple dot. So this expansion is valid for the modulus value of x less than 1. Okay, why? To ensure that the value for the 1 plus x always greater than 1. Okay, let's see the example. Expand the following: 1 plus x to the power of -2. So the question is easy because this the elements inside the parenthesis is exactly same with the original formula, and we only need to take note about the value for the n. So our n is equal to -2 because the value is -2, so that means we have to use this theorem in order to come out with the expansion. So we just simply substitute, okay, use this formula. We know our n equal to -2, so just insert our n equal to -2 into this equation. So finally we have this equation, and don't forget to write this triple dot, and then simplify this fraction. So we have the following equation: 1 minus 2x plus 6 over 2, which can be substituted as 3, minus -24 over 6, which also can be simplified as 4. Okay, so make sure you provide your answer in the simplest form. Okay, so it is equal to this equation, and don't forget to put this triple dot. All right, and also put this statement: this expansion is valid for the modulus of x less than 1. Okay, the modulus x is less than 1, in order to make sure that this expansion valid. Okay, this time also we have the value inside the parenthesis exactly the same as the formula: 1 plus x to the power of half. So half is belongs to the set of rational number because it is a quotient. So we have to use this theorem. Okay, we have to use this theorem in order to come out with the expansion. So we know our n equal to half. So just simply insert into the formula and then try to simplify the fractions, all the expressions inside the equation, and finally come out with the simplest equation. Okay, try to simplify all the fractions and come out with the simplest form. And don't forget also this triple dot, and then don't forget also this statement valid for the modulus x less than 1 to complete the answer. Next is 8 minus x equal to 1 over 3. Now it's different from the original form. In the original form of the formula is 1 plus x. Okay, 1 plus x to the power of n. So this time we have 8 minus x to the power of 1 over 3. So how to answer this question? First of all, we have to convert this form into the standard form, 1 plus x. Okay, how to do that? We do the factorization. So we factorize, we take 8 outside the parenthesis like this, and the remaining element inside the parenthesis is 1 plus negative 1 over 8x. Okay, so this is obey the standard form because this is 1 plus x. So that means the whole elements inside this parenthesis representing our x and must be substituted into the formula. Okay, must be substituted into the formula to substitute the place for x. And for the n, it is equal to 1 over 3. But then be careful here because we factorize 8 here. We factorize 8. And we also have this exponent outside the parenthesis. That means this exponent value also applicable to this 8. So that's why we have 8 to the power of 1 over 3 in front prior to this expansion. 1 plus negative 1 over 8x to the power of 1 over 3. Okay, so we find the expansion for this one and then we multiply again with this value. Okay, to complete the answer. So 8 to the power of 1 over 3 basically is equal to 2. Okay, which is the cube root of 8, which is equal to 2. So don't forget to put 2 outside the largest parenthesis. Okay, so now we back to this parenthesis. So we have 1 plus x to the power of n. So this is our x and this is our n. So just insert into the formula. Okay, the original formula. So we have this x, so we substitute this x with negative 1 over 8x. Okay, negative 1 over 8x. And then don't also forget about this triple dot. So as usual, try to make sure the final form is the simplest fraction. Okay, so try to simplify all the fractions in this parenthesis, and then don't forget to put 2 outside the parenthesis. Okay, so we simplify until we come out with this equation, which inside this parenthesis are in the simplest forms, and then we multiply with 2 and we obtain the final equation. Okay, so don't forget this triple dot, and also don't forget this statement valid for. So previously it valid for x less than 1, but this time our x is equal to negative 1 over 8x. So because we use the absolute value, so we can omit the minus, so it remains x over 8 modulus. So we need to make sure that we need to state that this equation valid when x over 8 less than 1, and then we also can simplify. It becomes x is less than, the modulus x is less than 8 can be taken here, so it becomes the modulus x less than 8 to complete the answer. So remember, don't forget to put 2 things. The first one is the triple dot, and the second one is this statement, the validity of this expansion. Okay, so the validity of this expansion, it valid for the modulus x is less than 1. So this time our x is equal to negative 1 over 8x. So simplify this one, and then we obtain the modulus of x less than 8 in order to this expansion to be valid. Okay, next we also have the form different from the standard form. So we have 2 plus 3x. The standard form is 1 plus x to the power of n, where n is negative or fraction value. So this time the value for the n is negative. Again, we have to make sure that we come out with this standard form. So just like the previous example, we need to factorize these two outside the parentheses. Okay, it is located here. So inside we have 1 plus 3 over 2x, which follow the standard form. So that means our x is equal to 3 over 2x. And then don't forget the negative one is located outside the largest parenthesis. That means it is also applicable for 2. So we take it to the 2, so it becomes 2 to the power of negative 1, which is equal to 1 over 2. And then we compute the expansion of this one. So we have two important informations here. This one is n, and also the value for our x is equal to 3 over 2x. So we substitute into the formula. Okay, so we obtain all the value inside the largest parenthesis. We simplify all the fractions. So finally we come out with this equation, and then don't forget to multiply with 1 over 2 to come out with the final equation. So don't forget about this triple dot, and also don't forget the validity statement. It's valid for x less than 1 because our x is equal to 3 x over 2. So write it as 3x over 2, and then we take 2 to the other side, and then we rearrange until we obtain again the modulus. The remaining value in the modulus is equal to x. So after we simplify this one, we obtain the modulus x less than 2 over 3. Okay, that is the final answer. Alright, thank you class. Okay, so that's the end of this lecture. Thank you.